We will now cover the mathematics behind gradient descent, which is the process of how the parameters of a machine learning model are learned. To cover this, we're going to work with our linear regression example, where, just to review, we have as input the hours spent studying, and we have as output the predicted exam score. So we're going to try to learn the line of best fit for these data, using stochastic gradient descent. And gradient descent follows a 4-step process outlined here. So the first step is to select random values for the model parameters. Because we're doing linear regression, those parameters are going to be m and b. We then calculate the mean squared errors for some values of m and b, for the pre-chosen values of m and b that we chose. Based on the error, we then update the values of m and b using some calculus. And finally, we repeat this process until the error becomes smaller than a pre-specified threshold. So we'll walk through this process in detail, and in particular, we'll go over the math, which does require some calculus, in particular derivatives. So if you're familiar with calculus, then this should be no issue. If you're not, then I recommend looking up just the intuition behind how derivatives work. If you don't have time for that, then very quickly in one sentence, a derivative measures the rate of change of a particular equation with respect to a particular variable. So let's look at this pictorially. So let's do the step 1 to choose the random values of m and b. So let's say we randomly choose m to be 0 and b to be 10. Then we start off with this dotted line as our initial line of best fit. Clearly it's not the line of best fit, but we have to start somewhere. So we have that line, initial line. So step 2 is now to calculate our error function, or our often called a loss function or objective function. In this case, we're going to use mean squared error, which is the difference between the predicted value and the true value squared. So we see in this table that we can predict all those values. We have the input x, the true value, the predicted value with our initial line, y equals 0x plus 10. And given our initial predictions and the true values, we can calculate the mean squared error by first calculating the squared error for every data point, as we see here, and then finally calculating the mean of these points. So we could just write that mathematically as the sum of the difference between the ith true point and the ith predicted value mxi plus b squared and divided by n because it's a mean or average. So that is mean squared error. We want to actually find the derivative of the mean squared error. The derivative will tell us the rate of change of the mean squared error as a certain variable changes. We want to know how the rate of change of the derivative changes of how the mean squared error changes with respect to when m changes and when respect to when b changes. So we can see that mathematically here. Just this is the derivative, so derivative with respect to m and derivative with respect to b of the mean squared error. So it's the same input. And so using derivative rules from calculus, we know that the derivative of this equation with respect to m is this equation, and the derivative of that same equation with respect to b is this equation. Don't worry about the specifics there if you've taken calculus. This should be obvious. If not, don't worry about it. Just know that there's a mathematical way to calculate the rate of change of an equation with respect to a certain variable in that equation. We then apply the update rule to our parameters. And we apply that rule using this update rule. So the new value of m is equal to the previous value of m minus some learning rate times that derivative of the loss function with respect to m, and same thing for b. Intuitively, this alpha learning rate tells you how quickly you want to update your parameters. If alpha is large, then you'll always make very large updates to your parameters. If it's small, you'll make smaller updates. And yeah, so we then, now that we understand the math, let's go into the detail of step 3, which is based on the value of the error, update the values of m and b. So again, we have our derivatives. So first thing we want to do is update the value of m. So let's look at our equation for the partial derivative of the loss function with respect to m, and that is, as reviewed, this equation up here. So we can calculate that for each individual point and then sum everything up. Calculating this, what goes inside of the summation for each point, summing them up and applying it into our partial derivative with respect to m equation and plugging everything in, we get a value of negative 120.9. If we do the same process for b, so taking the inside of that summation for the partial derivative with respect to b, calculating that inside of the summation for each data point, filling in the rest of the equation, we can get the same value for b, the partial derivative with respect to b. So we have negative 120.9 for the partial derivative of the loss function with respect to m, and negative 67.5 for the partial derivative of the loss function with respect to b. Now that we've calculated these numbers, we could plug it into our equation, and we get a new value for m and b. So the new value for m is 1.209, and the new value for b is 10.675. So our equation is now y equals 1.209x plus 10.675. And that gives us this line, which is not quite the line of best fit, but it's much better than our initial line. It's going closer to the line that we'll eventually want. It's not going quite as fast as it's not going super fast because our learning rate's 0.01. If we wanted it to go faster, we'd set the learning rate to 0.1 or something like that. However, if it's set to 0.1, then it'll make big jumps each time, and it might never get fine-grained enough to get a really nice solution. So in order to get it towards the line that we want, we apply this process iteratively again and again until the error, the mean squared error, is as small as we want it to be. So starting here, we do the same process again, but now starting with this initial value of m and this initial value of b, we repeat, we'll get a new line, we repeat, we get a new line. Eventually the new line will result in a loss or mean squared error that is very small, and then we know to stop. So that is the basic idea of how gradient descent works and how the math of learning model parameters works in general. So the same idea is applied in other types of machine learning, including classification. You just use a different loss function and, of course, different model parameters. Otherwise, it's the same intuition and the same process. If you found this video to be pretty quick, that is okay. On MLPro.io's blog, under the Learn tab on the top, you can access a blog that gives you, lets you read this information more slowly. So if you go to MLPro.io and click this Learn tab here, and you search in particular for gradient descent clearly explained, look for this blog post, and you can see what we just walked through in this video, but as text, so it can go a little slower and you can work through all the math on your own. So I hope this video was useful, and that concludes our deep dive and introduction into supervised machine learning. Thanks for watching. Bye.